Okay, so let's continue for the basic set theory. We're talking about, what is set, subset, superset, some basic set operations, for example, like union, intersection, complement, difference, what is disjoint, what is partition, right? So after that, right now let's talk about two laws. The first one is called the De Morgan law. This law says like this. So basically, it's a play involved with complement, intersection, union, those kind of like things. Okay, so for any sets, A1, A2, A3, etc. What it says it's A1 intersect A2, intersect A3, intersect Okay, let's see, up to AN. How about do this? Let's set it, and then I'm gonna do a complement. Okay. Remember the concept of complement. It's every element in the set S, but not in here, right? So how do we calculate this complement? Well, actually, this equals kind of like the distribution, but since it's complement, you can expect that the intersection is going to change. So it's going to give you this A1 complement union, A2 complement union, A3 complement union, and then union AN complement. Okay, so that's first part of the De Morgan law. Similarly, you can expect if we do a complement of the A union A2 union A3 up to AN, if you do a mimic, you can see it's going to be A1 complement intersect A2 complement intersect A3 complement intersect AN complement. Okay, so those two is what we call the De Morgan law. Okay. And also the other one is called the distributive law. So this is said like if you have three sets A, B, and C. Okay. So what it says is if you have the A intersect B union C, so you actually can distribute this A inside of this parentheses. That is A intersect B, and then union A intersect C. Okay, so that's a distribution. Another one, similarly like the De Morgan law, is if you have A union B intersect C, you can see it's going to be comes into A union B intersect A union C. Okay, so those are those two laws here. Okay, so that's should be very easy to talk about. And then next we can talk about what is a Cartesian product. Okay, so Cartesian product. So a Cartesian product of it's going to be two sets. Okay, Cartesian product of let's see, two sets A and B. So the notation here is kind of like doing a cross. Okay, it's actually it's the Cartesian product of those two sets. It will give you it's a set such that it contains the ordered, okay, this is very important, ordered pairs from A and B. Okay, so you can see that basically this is what we can describe this. So it's going to be an ordered pair, right? If we denote it as xy, such that, you know, x is an element of A, and then y is an element of B. Okay. So, for example, if we have set A, we have two elements. Let's say 1 and 2. Set B, we have 3 elements. Let's see, triangle, square, and circle. Okay, so if we do the Cartesian product of A cross B, as you can see that it's the ordered pairs, right? So we can write into the ordered pair starting with 1, right, and triangle, 1 square, 1 circle, and then after we got this, we can do 2 square, 2 triangle, 2 square, and then 2 circle. Okay, so you can see, yeah. So that's the meaning of this Cartesian product. Okay, the Cartesian product, and so you need to be very careful. Is first of all, these pairs, they are ordered. Okay, so yeah, they are ordered because the first part is going to be an element from the set A. Okay, and keep in mind is that A, the Cartesian product of A, you can call it A cross B, does not equal to B cross A. Okay, those are two different sets. Okay, so keep that in mind. And on top of that, you know, if our two sets are finite, so you can see if we can denote the number, for example, the number of the element in set A, it's kind of like an absolute value sign, okay, is equals to 2, okay, and then for this example, the number of elements in set B is equal to 3, right? So you can see that the Cartesian product set, which has 6 elements, right? So do you realize that it's the number of elements of A times the number of elements times B, right? That's something we can talk about. Okay, so that's one part, and then okay, the other part we can talk about is the another very important feature of being a set. It's called this is called the cardinality. Okay, meaning it will give us some distinction about the set. So if we talk about the cardinality, so let me write this down. So cardinality. Basically, we're talking about the size of a set. Okay, the cardinality. And then the cardinality of a set, how do we denote it? As you can see, we already know that, right? So, which is just like this. Okay. So based on the size of a set, we can distinguish our set into two types. If you give a set, it could be a finite set or a infinite set. Okay. And then apparently, if the set is finite, that means it contains the finite elements, right? If a set is infinite, it still have two categories. This one is called the countable. The other one is called the uncountable. So what's the meaning of being an uncountable infinite set? Well, for example, you have the natural number, right, set here. So you can see we can start to count it, right, the number of the elements. In fact, it's the perfect one, so 1, 2, 3, 4, 5, etc. So the definition of the countable infinite set is basically, you can think about it, if you can construct a one-to-one correspondence with a natural number, and then that set is called a countable set. Okay. For example, even the integer set, it's also countable. Why? Because if we reorganize this, our integer set into this, like 0, let's see, -1, 1, -2, 2, -3, 3, and then etc. Do you agree that we actually can build a one-to-one correspondence to the natural numbers 1, 2, 3, 4, 5, 6, 7, right? So you can see, right, there's a one-to-one correspondence to the natural numbers, right? So definitely this is countable. Okay. What are some examples that is uncountable? Well, so you can see the uncountable set, if we can think about this, real numbers. Okay, it's impossible for you to build a correspondence, one-to-one correspondence to the natural numbers, right? So not even for the real number system, but also you see, let's do this. What about the set from 1 to 2? There's no way, right, you can start to count it, right? So because there's always numbers between numbers. Do you see that? So that's what we call it. It's called the uncountable. Okay, uncountable. Uncountable. So yeah. So those are the two distinguish. You see, a set is going to be finite, infinite, and for infinite, it's countable and uncountable. Okay, so this is another example here. Okay. All right. So back to the finite set, which we're going to deal a bunch of them through this course, and then we have one principle. Okay. So for the finite set, actually, it actually can be extended for the countable infinite set, but we will put our restriction into the finite sets here. Let's see the inclusion, exclusion, principle. What it says is, so for any two sets, two finite sets, if we call it A and B, and then so this principle says like this: the cardinality of A union B equals the cardinality of A plus the cardinality of B, subtract the cardinality of A intersect B. Okay, so that's what we call this inclusion exclusion principle. Okay. And of course we can use this to extend it into a three-way. So you have A union B union C. The cardinality is going to be equals into cardinality of A plus cardinality of B plus cardinality of C, and then subtract the cardinality of A intersect B, subtract the cardinality of A intersect C, subtract the cardinality of B intersect C, and then plus the cardinality of A intersect B intersect C. Okay. So how do we actually we can explain this through the Venn diagram. Okay, through the Venn diagram. Basically, you see that, right? So this is A, this is B. So the A union B is this part. It actually equals, the number of elements in A here, and then plus the number of elements in B here. But don't you agree that this part, this intersection part, we actually counted it twice, right? So we need to get rid of that. So that is subtract this part. Okay. Now, similar idea, if we have A, B, C. Okay, A, B, C. So the cardinality of A union B union C, it's the set A, the cardinality of A plus the cardinality of B plus the cardinality of C. But as you can see that it actually counted the intersection of each two pair sets twice. So we need to subtract the intersection of them. Okay, but when you subtract the intersection of them, actually you subtract the intersection of A, B, and C already. So we need to add this back, and then so it will give us the total cardinality of A union B union C. Okay, so those are what we call the inclusion exclusion principles here. Okay, so I'll stop here for this part, and then hope you enjoy that. In the next session, we will provide more examples. Okay, thank you.